So I think I would like to start with a disclaimer as a kind of an apology. I'm a statistician, but I'm not apologizing for that. I'm apologizing because there's no max entropy word in my talk, okay? But that doesn't mean there is no entropy ideas there. So this is the disclaimer. As a statistician, I'm a very pragmatic statistician, so I used always different types of thinking, going from fiducial Fisherian inference all the way up to the most cutting-edge Bayesian methods. The spirit of what I understand, probably very limited knowledge of what maximum entropy is a kind of a way of solving an ill-posed problem, okay? And to me as a statistician, an ill-posed problem is when you have something you want to estimate something, for example, in the best case, or in the worst case, I would say, it would be the totality of the whole distribution of what you're observing under rather limited data conditions. And in the case of survival analysis, okay, so here, the data conditions are usually deteriorated by the fact of having sensory, okay? So that is the first idea, okay? So the second idea is that it's a way of solving statistical problems in that way. The way this presentation is going to be about, and the way of all of my work has always been done, is that you want to make a statistical inference not about the whole distribution, but about a parameters of interest you are interested, okay? So single target parameters, which can be as simple as just a one-dimensional parameter. I have done work in epidemiology, and the usual odds ratio, that kind of thing, is the target of interest, and we don't care necessarily too much about the whole distribution, but still we need to assume something, okay? So this idea of trying to assume something without making too many assumptions, again, goes back to these ideas of maximum entropy, okay? So you won't see anything about maximum entropy or entropy-related ideas, but the spirit, I think it follows very much that, okay? Something that maybe you have heard about the empirical likelihood. So the thing I'm going to present, it has very much that spirit. Okay, so let me just start then. And so an highlight of my talk is that if you want to classify this talk, then it would be in statistics, but in distribution theory, okay? And because of my background, this has to do a little bit with geometry, so then it will be mixed with geometry. So what I'm presenting here, it's a new functional approach, so there's going to be some maths, I'm afraid. In order to make estimation on the case of survival distributions using something called the cumulative hazard function, which I obviously will define. And the idea is that, obviously, with positive data, because we're going to be talking about survival times, death times, etc. So the idea is that this approach, the one I'm going to present, in some sense reproduce well-known survival models, simple but well-known survival models, and it can be used to generate new or extend those, okay? So let's just start with a very simple. I'm just going to start really from the bottom, from scratch. How do we characterize a probability distribution on the positive real line in this case? So we usually use things like density, okay? So most of the talks we have heard, they talk about densities, they talk about other elements. So this is only one of them. Under continuity, we have a definition like that, okay? So that's only one way to characterize the distribution under continuity. We can do it with the CDF, with the cumulative distribution function. That's another way, it's an integrated quantity. In some sense, it's slightly better than that because this is monotone, but this is monotone, but this is not. But there are other ways. So the other way could be, for example, the hazard function. So that's a quite popular way of characterizing distributions in survival analysis. By the way, survival analysis could be equally applied in context of reliability, okay? So the hazard rate function of the mortality rate, if you want to call it like that, even in other contexts, is another way to characterize distributions. And the other way, which is the one I'm more comfortable with and what this work is about, it's the cumulative hazard, which is just the integrated version of this guy. Okay? I'm not going to talk about the interpretation of that because, to be honest, it doesn't have a quite straightforward interpretation. At the moment, we're using this as a mathematical convenient tool. Okay, so obviously there is another way to characterize the distribution, which is the survival. It's almost the same as the CDF, as the cumulative distribution, just one minus that. But the thing which I want to highlight is this simple relationship. H I defined as being the cumulative hazard function. The exponential of minus that is the survival function, okay? So this is the way, just to show you, obviously, very simply, that the cumulative hazard function characterizes the distribution in this sense, okay? This very simple formula. So if we are given a cumulative distribution, cumulative hazard function, beg your pardon, H, then we can always recover the probability distribution associated, okay? So I'm going to work with capital H and not with densities or cumulative distribution functions or else. Okay, the notation I'm going to use is going to be a little bit unusual. Unusual in the sense that we use the twiddle to say distributions, but we normally put here the density or the distribution. But I'm going to put on the right-hand side of my notation the cumulative hazard. Okay? So that's just a bit of my notation. It's the distribution induced by this cumulative hazard function H, obviously using this formula. Okay? So in this talk, I'm going to focus on that. Okay? I already said that. So the idea is I'm going to try to think about the space of all possible distributions. I'm going to think about that in a kind of parametrization, which is the space of all possible cumulative hazard functions. And then just trying to use the fact that the cumulative hazard functions are always increasing, and that makes it relatively easier to study than any probability distribution. Okay, so that's the main idea. And then I'm going to see some structure, which I'm going to use to construct known models and then to generalize them. Okay, so just a bit of notation about models. Okay, so which kinds of things I'm thinking when I say simple models in survival analysis? I'm thinking about simple univariate models, nothing more than that, and also simple regression models. So simple univariate models like the exponential, okay? Well, that's the typical thing when you start explaining maximum entropy or entropy in the sense that it has a very simple entropy, for example, the exponential distribution. Weibel, gamma, log logistic, which I will define exactly what I mean by that, etc. So those are simple models in this univariate setting. In the regression setting, we have typical models as the proportional hazards model, which I would say is probably the most successful, or one of the most successful models in statistics in terms of citations. Accelerated failure time, this is more or less in order of importance. Proportional odds is not that used, but it's common. And one is very nice, but not many people know it, is something called the accelerated hazard. So if you're not familiar with those, well, I'm going to explain a little bit of what they are, but this is the kind of things I'm able to reconstruct and generalize. Okay? So here it is. So let's just a quick reminder of what this cumulative hazard function is. So it's just the integrated hazard. Okay? So the integrated hazard turned out to be something which is quite nice, but in order to make it nicer, and this is where the mathematically convenient construction is going to come in, we can relax this later. I'm not going to talk about this in this talk. But it's the following, okay? So this is always an increasing function because the hazard function is always positive, and therefore this maps 0 to infinity to 0 to infinity. So I'm going to think of that in a very pragmatic way as a time transformation, because T for me is always time to death, time to event, or time to disease, or whatever you're measuring as the survival time or death time, and therefore it maps. And these maps, it works well because we're making these are two real assumptions. So the real assumption translated to H0 is equal to 0, so 0 is a fixed point. And there is obviously no negative values, but because I'm putting the equality here, that means that there is no mass at 0, okay? So this doesn't include models with a 0 mass. So things like early deaths and things like that are not included, but as I said, they can be relaxed. And the other thing is Q models, okay? Because H of infinity is infinity in sense of a limit. So that means there is no mass at infinity, okay? So again, it's an assumption because it's excluding a few cases. And the other thing is also an assumption which is strictly increasing. So I'm not allowing to be constant, so the hazard rate cannot be 0 in some parts, okay? So anyway, I'm going to live with that constant because that's going to make me some mathematics. And the idea is that the cumulative hazard is simple. It's simple because it's increasing. So how many shapes you can think of without losing the assumptions which I said? So it has to be increasing. It has to be strictly increasing. So the typical behaviors, I would say, there are only 3, and then combinations of those. So one is being concave. Oh, sorry. One is being concave. The other one is being convex. And the other one is being a sort of combinations of both, because this is kind of concave here and then it's convex later. And then if you think about combinations of those, that's pretty much it. That's pretty much the kind of behaviors you can get in a cumulative hazard under my assumptions. Okay? So that's the idea in terms of using a mathematically more convenient object. are more manageable in that sense. Okay? Just examples, because those examples are going to come up all the time, are the exponential, as I said. Some of them are going to end up with parameters. Some of them are not, but you will see why. So the exponentials are going to put a parameter there, which is its mean or the reciprocal of its rate. Okay, so this is the cumulative hazard of an exponential. I'm going to be using cumulative hazards for everything. The y-ball is just a simple polynomial. It's actually a monomial, t to the theta. Log logistic is just that, okay? It's the logarithm of the exponential of a logistic distribution. Gompert is just something related to that. Instead of being logarithmic, it's exponential, so this grows quite quickly. And these are the simple ones, and I'm just putting this as a reference because this is almost like saying nothing, because this is just the formula, just a way of expressing the formula I show you for the gamma and the log normal, which they don't have a nice simple expression, okay? But they're still all increasing and have some kind of behavior in terms of convexity, concavity, or a mixture of both, okay? So I'm going to come up with this, so the notation I'm going to be using is hx, y, ll, etc. I'm going to be using sometimes that. So it would be good to have in as a reminder. Okay, so here is the spirit about the how to make inference when you don't know too much about the distribution and targeting specific parameters, okay? So I'm going to start with a basic construction, and the idea of the basic construction is stemmed from what is called a semiparametric family. Okay, so this definition of semiparametric families is a standard definition. You can find this in many books. And it's very open. It doesn't even think about estimation. It's just about a definition of a probability distribution indexed by its parameters. So when a probability distribution is indexed by real parameters and function value parameters, then we say it's semiparametric. So which means that we need to specify some numbers, okay, and some functions in order to specify our distribution, in this case, our cumulative hazard function. So simple example, and this example is going to be pretty much my running example. It's a regression example, but it's the simplest regression you can ever think of, which is two groups, okay? So pedagogically, that's the best way to start, maybe not mathematically, but to explaining regression, right, is the two-sample case. So imagine we have two samples. They have two distributions, which is characterized by H0 and H1. And then we want to see the relationship between these two via a model, okay? So in a nutshell, the accelerated failure time model can be explained by this, okay? So what this is, even to explain these kinds of models, the cumulative hazard function is simple enough to say something which sometimes in books you see this, at least they take him half a page to explain what accelerated failure time model is. It's just that, okay? So H1 is just H0 applied to some scale transformation of time. Proportional hazards model is basically the same, but the theta is outside. So I'm changing the scale on the hazard, not on the time, okay? And the other one is the proportional odds, which again is not very much used sometimes in survival analysis, but I think it's a very powerful model. It's just that, okay? And then you can see the idea is that if we apply the exponential on both sides, we're going to have something proportional to the exponential of h minus 1. And those are the odds, okay? Well, so let's continue. So this is an example of a regression model, and this is the kind of things which I'm going to do. So the parameters here, in this case, is just one simple parameter theta, because it's a two-sample problem. I only have one parameter. And the other one is the baseline cumulative hazard, right? Because if I have H0, H1 is determined by this equation. So this is a semiparametric, these are semiparametric problems, okay? So let's just see this visually. I mean, just so that we have a graphical and geometrical figure in our head. So we start with an H0, which we really don't know what it is, and we can be pragmatic and try to estimate that, as the Cox model does, or we can sort of assume it's in a parametric family, or we can just impose to be something specific. And then we're going to find some sort of direction, which it doesn't have to be linear, but I'm just doing the idea here of direction, which is determined by the parameter theta, to get us to the next H1, or if we can think of all possible thetas, that gives us a line or a curve. It doesn't have to be straight, in the space of all probability distributions. But of course, this space, I mean, it depends on if you want to enter topology arguments. It's a kind of a closed space, because there are some boundaries, okay? So if I go far enough, then I'm going to hit some boundary here. And we can see that here, if theta is infinity, okay, we can get a 0 there, and then we got a degenerate case, for example, okay? So that means if I go further here, then I'm going to hit a boundary, okay? So it's convenient to draw the space there. And the idea here is as a geometer, and this is what my contribution to my statistical problems is that I can think of this as a geometrical problem. So I need to be aware of the boundaries. It's a global problem, it's not a local, because I'm not going to think about derivatives. And even if I do, I need to be aware of large-scale behavior. So I'm aware of these boundaries, okay? So anyway, that's the idea. And then obviously you can put more parameters here, like more directions. And then you can endow this with notions of orthogonality and stuff like that. And then basically you got a frame of reference there, okay? So, but I'm not going to do that. I'm just going to keep simple in this case. Okay. So, what are my building blocks? So, because remember, the idea of this talk is to give a framework to construct distributions using cumulative hazards. I just give you examples of models which does exactly that in terms of simple lines. So the idea is just a composition. So such a simple operation, we'll see that it's actually very powerful in this sense and gives me a very simple way of reconstructing models. So the idea is, imagine, I guess, again, I have two cumulative hazards, H0 and H1, and I think about of one of them as the baseline. So Z is like my baseline time, or it could be the time of my first group, the time of death of my first group. This is a random variable. And I'm going to think the second one as a transformation of time, okay? Because remember, H is always something increasing. Its inverse is going to be increasing as well. So it doesn't matter if I look like this or if I look like this. This is a transformation of time. And therefore, the distribution of T is going to be the composition of H0 and H1, okay? So that means if I composed, and I've been in composing, I mean just mathematical functional composition of two functions, I stay inside the space of probability distributions, okay? So that's a kind of a safe way of moving around the space of probability distributions, which is what I want to do. And just be careful of boundaries, etc. That's another issue which I will address, but that's the kind of idea, okay? Composing has two nice properties. One is very easy to compose. I stay within the probability distributions without worrying about it. And second, I can interpret this as a transformation of time, okay? So accelerated failure time models is well known for being a transformation of time. So if we have two groups, one, it's an acceleration or a deceleration of the time of the others. It can be dying faster or dying slower than the other group. So that's the idea, and yet we're generalizing this here with a very simple mathematical object. Okay? So compositions of cumulative hazards are cumulative hazards. That's the message. Okay? So let's just see. I'm just going to see the example I've done. So the first example is, if I start with a baseline cumulative hazard, and I apply the simplest transformation you can ever think of, which is the inverse of the exponential, which is just multiplying by a constant, what I'm doing is adding a scale parameter. So I'm just trying to see that the trivial examples of endowing a distribution with a scale parameter can be reconstructed this way. So that's obvious, let's say. And scale parameter, which if I think of this as the link function for some covariates, then it's an accelerated failure time model. If I do this transformation, which is just the inverse of the y ball, the power of 1 over theta, then the fact of doing that composition, it's like adding a power parameter, okay? And why power parameters or scale parameters are important is because if we think of the log transformation and making time transform it to the real line, this corresponds to a location and scale, okay? So that's the simplest operation you can ever think of in a probability distribution in order to generalize the distribution of that, okay? So that's the first example. Obviously, if we think of H0 being already exponential, I'm doing nothing. I stay inside the family. If I think of H0 being y ball, I also doing nothing because it's just adding the exponents, and here I'm multiplying the denominators in the two cases. This is if I know H0 to be either exponential or y ball. So these two distributions are special because are going to be the equivalent, we know that, as the normal distribution has in the real line. It's closed under an enormous amount of operations. Anyway, so that's just by the by. And this is not a known model, but I can start playing. So I can transform time by a constant, but then transform it non-linearly with some function. For example, the log logistic, which is like adding the exponential, and then I get something like this, which is not a known model, but I know that this is going to give me a probability distribution in which theta is a parameter, and I know what it means, and so on and so forth. Okay? So that's just an example which doesn't have any specific application, but that's the way I'm going to start playing. Okay, so let me see how do we with time. Okay. So compositions, but look, there is an asymmetry here, which in some sense is good and bad, as always. That the way I did the composition and the interpretation with the transformation in time, it only worked in one way. And the one way is it worked for this composition, H0 and H1, not for the other. And it's not allowed here to just swap the names of things, because otherwise time is no longer time, it would be something else, okay? So the asymmetry here, I'm going to respect it as it is. So one thing is the time, the other thing is the transformation of time. And then it's not obvious how to interpret the other composition, right? When H0 is inside, not outside, okay? So examples of that actually gives me just more models, okay? And all of the models I'm putting on bold letters are just known models in survival analysis, okay? So the other one is when I do a power, but now I do it outside the hazard, I stay inside because a power of an increasing function is increasing function unless theta, I assume, is positive. This is called a hazard power parameter, okay? So that's just a way of generating a semiparametric family. A very popular one in survival analysis of frailty, okay? And this case is the fixed version, not the random version. If I do the exponential instead of the Weibull, what I get is something called a frailty parameter. When I'm going to talk about the random case when theta is random, and then you get something which is heterogeneous and so on and so forth. But still it's called a frailty parameter, okay? Well-known model. It's also reconstructed by a simple composition. Okay. And the other one is the proportional odds model. Sorry, I didn't warn you about this abbreviation. This is proportional odds model, proportional hazards model. Is when I do this slightly more elaborated composition of the log logistic and the Gompertz. With this parameter, it's almost like one and the inverse of the other. I get something which is known as the tilt parameter, and this is exactly the proportional odds model. Okay, it's the way I just described it before. Okay, so just emphasizing that what I'm doing here is just reproducing known models using my approach of compositions. Okay. So now let's just see the random case, which I think is interesting. So the random case is when you have frailties, which is just a constant multiplying the hazard function or the cumulative hazard function, but it's random. And the interpretation of that, which is actually quite well used in applied research, is that this reflects the heterogeneity. All of the individuals you are seeing in the group, they're actually heterogeneous, but you haven't measured the variables which make them heterogeneous. So you're going to use this hierarchical model or mixture model if you like. Okay? So the idea is that now conditional on theta, we have something which multiplies the baseline hazard. And the idea is, and this is a result which we have, it's a very simple result, is that the marginal distribution of T is actually a composition. Okay? Another simple composition of T, HM composed with H0. Okay? But the trick is, this is only if and only if HM is a Bernstein CH function. And a Bernstein CH function it's just a Bernstein function, which is a Bernstein, I'm going to define it in a second, but it's just something very related to complete monotone. Okay? So it's something slightly difficult to get in the sense that not many functions does it, but again, from the point of view of simple models, we can find enough Bernstein functions which do that. Okay? And then we'll see what is the trick here. The trick is that HM is not the CH function of theta, okay? It's not that, it's something else. It's related to its Laplace transform, okay, but it's not that. But it still is a cumulative hazard, and I just can come up with a Bernstein's cumulative hazard, apply it, and automatically I've got a mixture model, okay? Without checking that it's a mixture, without integrating anything. So a CH function is, as I said, is very similar to a complete monotone, except that the signs of the derivatives are shifted one number, okay? because here I need to be positive on the first derivative, because remember this is increasing, and then after the signs of the derivatives are alternating. So, what is the message here? Composing, we can compose as an operation instead of integrating, okay? So one option is integrating, right? Because this is a conditional model, this is the marginal model. If I know the distribution of theta, then I need to integrate that distribution in order to get that. But what I'm saying is, if we have that property, then we can just apply a simple composition, and I've got my mixture, okay? Or I've got my frailty model. Okay, so that's one idea. And as I said, if you go into the literature of Bernstein function, which is unexplored for statisticians, there is quite a lot of distributions there which are actually quite nice, and which can just use and just borrow. Okay, so that's one of the contributions of my work. So the other thing is, which is obvious, is if you work out the other derivative, the first one needs to be positive, the second one needs to be negative. So they are concave, okay? Because I'm assuming they are all nice and smooth. So if you think about composing with something which is convex, it always has this mixing effect, okay? That means the variance is going to increase and that kind of thing. So that's a kind of a nice interpretation of the composition as well. We know what it's doing in this case, if we have concave cumulative hazards. I'm going to go quickly, but this is just one example from the statistics literature. There are examples from the non-statistics literature of a family which is called a power variance frailty distribution, which recovers simple cases and which is Bernstein, okay? I'm going to say that this Weibel and this log logistic, as I said, are not the distributions are not the mixing distributions, because the cumulative hazard, this HM, is not the cumulative hazard of the mixing distribution, it's something else. Just artificial Weibel and artificial log logistic. It's basically the space of all Laplace transforms, okay? That's what it is. Okay, so I'll go quickly there. So the other one is an inverse. So compositions, let's just forget about that for a second. Now let's think about inverses. And I already anticipated that the inverse of an increasing function is increasing. So I don't lose that property by making inversion. Okay, so we can interpret that. This is slightly cumbersome interpretation. It's another transformation of time, sorry. It's another transformation of time, but it's applying the same thing twice, H0 twice, and then the distribution, the marginal distribution of T is the inverse. Okay? So what it means is that inverses of cumulative hazards are cumulative hazards. I mean, to be honest, this proof is actually a little bit ridiculous, because we know that the inverse of an increasing function is an increasing function, but at least it gives us an interpretation, which is, in this case, we haven't found a good way of explaining, but it's a way of explaining what it's doing. Another transformation of time. Okay? So inverses, again, the exponential and the Weibel are close on their inverses. If I take the inverse of the cumulative hazard of the exponential, I get just another exponential. If I take the inverse of a Weibel, I just get another Weibel. So I don't go out the family, okay? And so, but others are just inverses of each other. So the log logistic I put on purpose is just the inverse of the Gompertz, okay? This is convex and the other one is concave, okay? So well-known distribution, they turn out to be one is the inverse of the other in this cumulative hazard sense. And all of this information, to be honest, is in the literature in a case-by-case thing. So you see all of these facts just like for the Gompertz or the log logistic or for specific cases, but basically one of the contributions is to put it all together in one single approach. Okay, so this is what we're trying to do. Obviously, if H is convex, H minus 1 is concave, and so on. Okay, so, and then I'm going to play with that. That's going to be my key ingredients. If I got H, I can always calculate H minus 1, even numerically, and then I can mix them up in order to create something which is neither. Okay, that's going to be the idea. There are other examples which I'm going to skip just for reasons of time. Okay, I'm going to skip those. It's just yet more examples. So let me see. Now regression models. So those were simple univariate models. So let's just see now regression models, which are neither of the ones I just described. I described the proportional hazards model in the simplest case, the accelerated failure time model in the simplest case, but there are others which are used very much in clinical trials and epidemiology, and these are really important and useful models. So there is something called the Young-Prentice model. I mean, it doesn't have a specific name, but basically we can write as a composition in terms of two parameters now instead of one, okay? And the idea is generalizing the other models. So this, for some values of the parameter, is the proportional odds. For some other values, is the proportional hazard. So the idea here is that the proportional hazards assumption is quite strong, and in practice, many things don't have proportional hazards, okay? So obviously, it's always good to entertain models which consider the case in which the groups have proportional hazards, but obviously the cases when it doesn't, okay? And this is a case which if it's not proportional hazards, then it would be proportional odds. And then we can keep playing this game. So this model is not written in this way in the paper, but we're writing it way. So we can just play because now we know how to do it, okay? So this is when you teach a kid how to use something, a computer, a gun, or a car. They can actually use it. They don't know what they're doing. And to be honest, this is exactly what's happening with us. At the moment we're at the kid stage and we have a machinery and we're starting to learn how to use it. So this is a way, a nonsensically way if you like to use it. So we can mimic this is not the same to say, okay, let's just generalize the proportional odd models and the accelerated failure time model. We haven't found a model which combines these two in a general sense by doing our compositions, okay? Just by composing cleverly, if you like. That's the idea. Okay. Many possibilities there. Are more building blocks, which of course I don't have time to discuss, but this is the typical ones because this is much more in the literature about that. Sums of cumulative hazards are cumulative hazard. This is super studied in terms of reliability because this is related to coherent systems and minimums of random variables and so on. This is what it is. So I'm not going to talk about that. Product sort of is. The product of cumulative hazard is a cumulative hazard. Maxima is always a cumulative hazard. You're starting to get problems because this gives you non-differentiability and so on. But anyway, and the one which I found fascinating is this. Indefinite integrals of cumulative hazards are cumulative hazards. So the indefinite integral of an increasing function is again an increasing function. And then we can just play, okay? So this is the one which at the moment we're exploring more. I'll talk about this at the end. So what we want this for, okay? So the idea is going to be the following. So in one of the previous talks, somebody talked about exponential families. And mixture models is also kind of a very powerful way of doing statistics. Kind of a basic, if you like, not very modern, but quite classical and quite powerful way. So exponential families and mixture models as a kind of a way of now not generalizing one distribution, but two, okay? So this is what I'm going to do. Imagine I have two distributions, P1 and P2. Sorry, there's a typo there. And so let's think about how we can construct a family which contains P1 and P2, okay? So the first one is doing a mixture, okay? Simple. Convex combination of densities is a density, okay? Exponential family, maybe not many people recognize it that way, but it's a geometric combination of densities. That's actually my way of understanding what an exponential family is you take two members of the family, compose them geometrically, and you generate the family again, okay? So that's another way, well known. The natural parameter is always that, because it's related to the log likelihood ratio. But the other way is doing it using cumulative hazard, which is what, using our building blocks, we're going to do that. So we can do convex combinations of cumulative hazards are cumulative hazards, just following what I said. Geometric combinations of cumulative hazards, again, are cumulative hazards. And then we can keep playing, sorry. And the other one is maxima. In this sense, it's also a cumulative hazard. Okay? But I'm not going to talk about that. But this is just the analog of the exponential families and the exponential families. Okay? The one I'm going to talk about a bit more is this one. Okay? So this is at the moment our preferred one. Another weird composition, but it works quite nicely. So, simple case. Let's just think about that. If theta is equal to 0, okay, it's not obvious because I get an indeterminate case, right? It's 0 in the numerator because h of the cumulative hazard at 0 is always 0 divided by 0. But if we use L'Hopital rule, okay, then we always get the thing inside, is h1, okay? So this is h1, and basically dividing by theta removes that indeterminacy which I talked about before when we take h of 0 is always 0. And the other one is when theta is equal to 1, I'm composing with its inverse, and then I get h2, okay? So this is a way of constructing a distribution which contains two given distributions. Obviously, I need some conditions. So for example, the Weibel doesn't work for this, but the Weibel is simple enough that I don't need to do that. That the actual hazard, not the cumulative hazard at 0, needs to be positive, okay? So that's some kind of a restriction, so it is what it is. Sorry. Okay, so this is the kind of compositions we can do with our, combinations, let's call it, with our approach. Another advantage is that we don't have to be restricted to be between 0, 1, as all of the examples I said before, okay? 0, 1 have an interpretation, and between 0 and 1 is like being in the middle, but I can be bigger than 1, and that's not a problem. I stay within the space of probability distribution, okay? Okay, so there's more about that. I'm going to skip that because there's a bit more detail. What I'm interested is in this case. The case I'm interested is when H1 is a hazard and with H2 it's inverse. It's inverse. And what I'm doing that is because if I choose H1 to be convex and H minus 1 therefore is concave, if I mix them up, I'm going to get things in between, and that gives me some flexibility. That's the idea. Okay? So if I do that with the linear combination or convex combination, I automatically achieve that without having to worry about any parameters or boundaries. If I do it geometrically, the same. Theta has to be between 0 and 1. That's the only thing. If I do it with the maximum, and if I do it with my approach, I get some, this is not a typo, I need to apply the H minus 1 twice, okay, in order to get the limits again. So for theta 0, I get H, and for theta 1, I get H minus 1 or the other way around, okay? So I include the distributions I have, and I can play with that for theta larger than 0. So in general, I mean, I put this as an example, but in general, the idea is just what I said. I'm just going to put this in general. So if I have something which is concave and something which is convex, that means that the hazard function is increasing or decreasing, because the derivative it would be either positive or negative, second derivative, and therefore the hazards of those things are always increasing or decreasing, but when I mix them up, I can get things like bad tubes or unimodals, or even more. If I can start adding more things, then I can get things which have multimodal, which again, it depends on the application if you want to go that way, okay? I'm not saying this is just for the sake of doing it, but you can start think about what you're doing now. Okay, and then you can do that always for any of the combinations I presented. Okay, so for example, this is just an example of things you can do. Oh, what we're doing. This is a combination of that kind, okay? So this is the combination which I just presented, the last one, using H and H minus 1. If we do it with the Gompertz, okay, sorry, I changed here Lomax, I mean the log logistic is just another name, you can find it on the literature. If you do this kind of composition, you can get some distributions which are either very weird or interested in some sense, interesting. So this one, for example, is a distribution with super heavy tails, as you would imagine, because the exponential of minus that is going to come up in the density, and you got a log, iterated log of this with an exponential. So it's kind of a logarithmic thing, but not quite, because it's a combination. And this is, for example, we have been using this for obviously modeling some high heavy tail data, or also to model some kind of prior distributions, which is good, well, it's been seen as good nowadays, having prior distributions which have heavy tails and don't have moments. This thing doesn't have any moments, any positive moments, for example. So for priors, that's actually very good, okay? If you have a prior which has a long tail and no moments, it's actually been seen good if you really don't know anything, okay? I'm going to go into that discussion of reference prior, but it's a kind of a good prior to use. People nowadays use half Cauchys and have these kinds of things, and this would be the equivalent of that, okay? Anyway, so that's one example of things we are doing, okay? And convex duality, okay, so that's the last thing I'm going to talk about. I have a few more slides, just a couple of slides. And that there is actually more things which now we're trying to put together. The problem is that the more we start exploring, the more new operations with these cumulative hazards appear. So the new one is this one, okay? So without looking, we found this idea of conjugacy, but outside the convex world. So you can always define the convex conjugate even if the function is not convex, okay? It's just solving that optimization problem. Okay, it's always, the conjugate is always convex, and it's always a cumulative hazard, okay? It's not as nice because I think we go out of our space of cumulative hazards, which is nice and well behaved, or with the assumptions we have, but I think it's a good start. And we can iterate again to have the biconjugate, as a kind of a convexification of the original one, okay, if we want to go that route. Of course, if the function is convex, everything nice and easy. For example, this is a convex function, the integrated cumulative hazard, and the conjugate has a simple form, it's just the integral of the inverse, and the biconjugate is the same function, okay? So if we have convexity already, we know the theory that the biconjugate is going to give me the same. So this gives an idea of maximality here, right? So, because we cannot get out of the set. And then we're trying to explore this for certain kind of problems. Okay, so I think that's pretty much it. I have something about estimation which I don't have time to explain, I'm afraid, because I run out of time. So the conclusion or the discussion, if you like, is the following. So we have a very simple, but I would say yet powerful in the sense that we can reconstruct lots of many known things, way of constructing models, okay? It's a good compromise between simple parsimony models like the ones we started with and something, you know, the usual nowadays people do Bayesian non-parametrics with these kind of problems. I think this lies in the middle, okay? I didn't have time to talk about inferential properties, but the convexity I talk about gives me some convexity structure, which is good for computations. In some cases, I get log concave likelihoods and so on, which are good, okay? So, but this is just obviously something which is from the point of view when you have data. And in some sense, we are very excited about doing this, and I will be very happy to take any questions. Thank you very much indeed.